Hello everyone, welcome to Mechanical Engineering Design and Innovation course. Myself Dr. P. Rajkumar, Assistant Professor, Department of Mechanical Engineering. The topic for today's discussion is brittle and ductile material failures. So the aim of the present session is to make you to understand what do you mean by brittle material, what do you mean by ductile material, and how to identify the brittle and ductile material failures. So at the end of this session you will be able to understand the concept related to brittle and ductile material failures. So as I already told you in the previous session, this is the stress strain graph for the ductile materials. Here you can see the ductile material I am considered here is the mild steel. So whenever you are subjecting this to the tensile loads, then initially the applied load starts from here and it will slowly increases, the applied stress will increase, and here till here it will be proportional. That means the stress and the strain will be proportional till this point. That is why this point will call proportional point. And if you extend this one, we will be having some 0.02 percentage of permanent deformation. That value will be given here within this zone. And this, if I further extend the applied load, then it will be still in the elastic limit. That point we will call E point. So once if I remove the applied load at this point, the material or the component will come to its original shape. So that's why that Hooke's law is applicable till here. And then if I load further loading, then it will enter into that plastic zone or deformation zone. Y1 and Y2 will call yielding points, upper yielding and lower yielding points, and you will call, and if I further load, then the component will be in the plastic zone. That means it will deform and at the EU, ultimate tensile, ultimate strength. So whenever the component is loaded till here, then it will subjected to failure. So that point will be known as F point. So F indicates the failure point. So whatever the energy, if I extend the one line here, if I calculate the area or the under this, the area under this will gives me the toughness, and if I calculate the area under only till elastic point, that will give me the resilience. So this is how the stress strain curve looks for a ductile material. If whenever you are testing a material, let's say if you are testing a material, that means mild steel, if you are testing it under tensile load, then you will get the stress strain curve like this. In other case, if you are testing any of the brittle material in the tensile load, then you will get the stress strain curve like this. That means it is not giving any the yield deformation. The brittle materials are failing. Once the crack is initiated, it is immediately getting failed. There is no plastic zone in the brittle material failures. So the brittle material, you can take the cast iron. So once it will withstand the load till its capacity. Whenever small crack is induced in that material, then if you apply the load, then immediately it will cause for failure. So ductility and brittleness, we already seen the definitions. Ductility is defined as the ability of the material to deform to a greater extent before the sign of the crack. Whereas the brittleness, it is a property of the material which shows the negligible plastic deformation before its fracture. So even though you cannot find out the clear cut plastic zone for a brittle materials, you can say there won't be any plastic zone or negligible plastic deformation will be there for the brittle materials. So how we can find out whether the material is a brittle failure or the ductile failure? If I get my tensile loading, if I get my stress strain curve like this, then I can say the material is subjected to ductile failure. If I get the stress strain curves like this, then I can say the material is subjected to brittle failure. This is with respect to your stress strain curve. And with respect to the microstructure, if I get the microstructure, the failures, if I get the cup and cone shape, then I can say the material is very ductile. If the material is moderately ductile, then I will get the fracturography like this. And for brittle material, it is like flat without any So in a nutshell, if I get the cup and cone shape in my fractography or the some examination, then I can say the material is subjected to the ductile material failure. And if I get the failures like this, I can say the brittle failure. So we will see some of the SEM, scanning electron microscope images. This is the actual samples that is subjected to the failures. So here you can see the cup and cone. Here you can see this is one part, this is another part. So it is like one cup shape, another it is like cone. So cup and cone failure I am getting. So I can say these materials are subjected to the ductile failures. And if I see here it is like flat, so I can say it is like brittle failure. So the brittle failure, as I told, it is a can be cast iron as or ceramics. The examples for the ductile materials is the aluminum. So whenever if you test aluminum for the tensile loading, you will observe this kind of cup and cone material failure. And whenever you test ceramics or some cast iron, you will get this flat failure. So if you see here, the brittle failures, like different small pieces you can see. Whereas in the ductile failure, only one failure you will see here. But the thing is, even though here large number of pieces are there, there is no information, there is no clue why we got so many small pieces. Here even though it is one piece, we have large information, that is it started from here and it is extended till here. That means we have some plastic deformation zone to identify the ductile failure. Whereas here we do not have any of the plastic deformation zone in the brittle failures. So here you can see, you can observe here, as I already told you, that ductile failure will slowly start with the necking phenomena. Necking phenomena is the reducing the size of the cross section. Slowly it will start with the reduction in the cross section area, that is necking. Then it will slowly start with the nucleation, small nucleations, that means small voids. Then with the further loading, this voids will be connected and it will create as a linkage. And if you further loading, it will cause for the shearing, okay, and at the end you will get the fracture. The fracture is like cup and then cone, the cup and cone phenomena. It is the scanning electron microscopic image for a particular material, and using this material, using this image, we can say the material is subjected to the ductile failure. You can see here the brittle material failure, it is directly one straight line we got. But we do not know why this material has failure. So it is like there is one arrow, this arrow indicates the failure originated, from where the failure is started, okay, from where the failure is started and how is propagated. So only the starting point we can understood, from here this is started and it is extended, but there is no deformation, it is directly. Whereas here in this image we have cup and cone phenomena. So with respect to this we can say it is a ductile failure. But here with respect to this straight line, we can say it is a brittle failure. So for the brittle fracture, there is another or some more, the scanning electron microscope images. You can see here the ceramics, how it is like steps, and the steel here like cracks, the flat region, the crack, it is for polypropylene. So for these are the different materials the fractography studies. So what is the first thing? Either using the stress strain curve, we can say whether it is a brittle failure or ductile failure. Then the next one is the cup and cone or the flat failure, we can say. And the third one by using the scanning electron microscope images, or by using the fractography study, we can say whether the material is subjected to brittle failure or the ductile failure. So we can see what are the characteristics of the brittle failures. So you can see in a brittle failure, there won't be or little or no plastic deformation zone. This is one of the characteristics. Suddenly they will be subjected to the fracture without giving any indication. Brittle fracture, that means they won't give any prior indication that okay, I am going to failure, like that. It won't give any prior indication. Why? Because if we have the yielding zone, then we can see that using that voids we can say okay, the material is going to failure. But whereas the brittle materials, they won't give any prior indication. That is one of the characteristics. And the low energy absorption, as well as if you apply the more load, let us say for example you have applied 10 kg, okay, the material is withstand, 100 kg it will withstand. If you apply the 10,000 kg, so it will won't give any indication, it will directly fail. That means the low energy absorption, and but this material will be having the high stiffness, that means high E value they will be having. So all these are the characteristics of the brittle materials. Now similarly, coming to the characteristics of the ductile materials, they will be having the extensive plastic deformation zone, and we know that the necking phenomena will happen in the during the ductile material failures, and ductile fracture moderate, they will be having the moderate stiffness value. So these are the different characteristics of the ductile material failure. Let us see some case studies on the brittle material failure as well as the ductile material failure. Now I am considering the brittle material. Let us say I am considering the some skylight glass I am considering. So this some skylight glass panels are used for the to enhance the strength and the safety features in some commercial building they have used. This is the problem, but it is subjected to its weight and some accumulated snow and some live loads from wind and occasional maintenance activities, some loads. So this glass is subjected to the snow loads as well as the live loads from the wind, but the design engineer not considered all these loads while designing those glass panels for a commercial building. So because he has not mentioned, he has not considered those loads during design, it will immediately lead to the failure without giving any prior indication. Even though you have considered other factors, since you have not considered these load factors which can cause the brittle failure, then that entire component or entire product may lead to the brittle failure. So that's why during the design we have to consider what are the factors that may lead to the brittle failure and ductile failures. Okay, since if we consider these factors and if you redesign these components, then it may not fail for those loads. Okay, so while doing the brittle material analysis, you have to consider what are the loads or what are the loads that may cause for the brittle failures you have to consider. And this is another case study on the ductile materials. Here I am taking some steel component I am taking, but this steel component, the design engineer did not consider the cyclic loadings that are acting on the steel component. So since he has not considered, what happens, the loads, the cycling loads can cause for the microscopic cracks which can further leads to which will further extends, and they will initiate and propagate further, and finally they will lead to the failures. So by seeing that failure mechanism, we can say yes, this steel component is failure to the ductile failure. Then the design engineer will understand, okay, why the ductile failure has happened, what are the reasons. So at that time he will understood, since this component is subjected to the cycling loading, and as a design engineer no one has understood, no one has designed the cyclic loading for that component, so that's why it got failure. So in conclusion, what we have to do, whenever we are designing a component, we have to ensure what kind of material or what kind of loads that component will subject, and how I can arrest and how can I extend the life of the component without subjecting to the failure. So as a design engineer, everything we have to consider. So we have seen the one case study on the brittle failure in the commercial building, some glasses, and in the case study 2, that is on the ductile material failure for a structural steel component subjected to the cyclic loading. So till now we have seen how to identify the brittle material and ductile material failures using stress strain curve, using cup and cone and flat material, using microscopic structures, and some case studies on that we have seen. So these are the different material textbooks and references for your further learning. Thank you.